Welcome to the deep dive. Today, we're really getting into the nitty-gritty of injection molding quotes,
That's right.
our mission, to give you the knowledge you need to get accurate pricing and, dodge those common pitfalls. We're using a solid guide on what info molders actually need.
Absolutely. And getting that quote right isn't just about the dollars and cents, is it? It's fundamental for planning, hitting your timelines, and ensuring part quality.
For sure. Especially since the mold tooling itself is often a major upfront cost. Precision from the start is key.
And that precision comes from a detailed request for quotation, the RFQ. If you give the molder all the details, you minimize their guesswork.
Which means they don't have to inflate the price just to cover unknowns, right?
Exactly. They can give you a much sharper, more competitive price. It's surprising how often incomplete RFQs cause headaches.
Yeah, I read something like, up to 80% of orders hit unexpected costs, often because something was missed early on.
It's a huge number. Simple misunderstandings lead to bad quotes, delays, cost blowouts. It can even sour the relationship with your supplier.
Okay, let's talk specifics. Like, if you just vaguely ask for general-purpose ABS, what happens?
Well, the molder might quote the cheapest grade they can find, but maybe your part needs UV resistance or higher strength. If it doesn't meet the need, you're looking at part failure, maybe even a total redesign. Costly.
Okay, that makes sense. Or forgetting critical tolerances.
Same problem, different angle. They'll assume standard commercial tolerances. If your part needs to fit precisely with another component, it just might not work. Then you're stuck with rework, or worse.
And tighter tolerances mean more cost up front, yeah.
Right. More precise machining for the tool, maybe slower cycles, more careful process control. It all adds up.
Volume 2, right? Quoting for the 1,000 parts versus 100,000 annually. Totally different game.
Huge difference in the per part price, and maybe even the type of mold they'd recommend.
And documentation. A 3D model alone isn't always enough.
It's essential, but you really need a 2D drawing too. That's where you put things like GD&T, geometric dimensioning, and tolerancing. Without that, the molder's guessing on critical fits and functions.
GD&T sounds technical, but it's basically the rulebook for acceptable variation.
Exactly. It's like the contract for dimensions. Avoids arguments later about whether a part is good or not.
What about looks? Like surface finish?
Another easy miss. If you don't specify, you'll likely get a standard machine finish. If you wanted something polished or textured, that's extra cost added later, potentially delaying things.
And, this is a big one. Forgetting to mention you already have a mold you want to use.
Oof, yeah. You'll get quoted for a brand new tool, which is way more expensive. Or sending the wrong CAD file version. Nightmare fuel. Building a tool to an old design is disaster.
Okay, so the takeaway is, a detailed RFQ isn't just paperwork. It shows you're prepared, gets you better attention, and leads to faster, more accurate quotes.
Precisely. It sets the stage for a good partnership.
All right, let's dive deeper into that core part information. What's non-negotiable?
Clear, unambiguous communication is the foundation. And that starts with really solid design documentation.
The 3D CAD model is central, obviously. You mentioned STEP and IGS files.
Yes, STEP is often preferred. It's generally better at keeping all the solid geometry data intact, which is what mold designers need. You definitely want a solid model, not just a surface model like you might get from, say, an STL file meant for 3D printing.
Right. STLs are more like just the skin.
Pretty much.
Mm-hmm.
And make sure it's the latest version. Clear labeling, rigorous version control, saves so much potential pain.
And the 2D drawings supplement that 3D model, PDF, DWG, DXF. That's where you call out the really critical stuff.
Exactly. Critical dimensions, the material spec, surface finish, and that GD&T we talked about. It specifies exactly how much wiggle room is allowed for form, fit, and function. Any vagueness here spells trouble.
You also need things like draft angles specified.
Yep, those slight tapers, so the part can actually pop out of the mold. Usually need at least half a degree, maybe more if there's texture. And undercuts features that block a straight pullout need clear identification. They mean complex mold actions like slides or lifters. Big cost driver.
Makes sense. And calling out CTQs. Critical to quality features.
Yeah, or CTMs, critical to manufacture. If a certain diameter is vital for assembly, say it. If you know a thin section might warp, flag it. It helps the molder focus their DFM design for manufacturability analysis.
So being upfront about potential issues helps them plan.
Definitely. They're going to do a DFM review anyway, but a well-considered design with potential issues flagged just speeds everything up and leads to a better outcome. Physical samples can help sometimes, maybe for texture, but they're no substitute for good digital data.
Okay, beyond the drawings, defining the parts job.
Crucial. How will it be used? What's the environment? Chemicals, UV, heat, cold, humidity, mechanical stress. Is it part of an assembly?
And regulatory needs, right?
Yeah.
Medical, automotive, etc.
Absolutely. A part for a medical device has way different requirements and documentation needs than, say, a toy. This context drives material choice and design validation.
Then the geometry details. Size, weight, complexity, wall thickness is a big one.
Huge. Keeping wall thickness uniform is key to avoiding sink marks and warping. Ribs should generally be, 40–60% of the main wall thickness. Specifying draft angles, identifying undercuts, maybe even suggesting a parting line location.
And tolerances again. Specify general ones, but highlight the critical ones using GD&T. Don't over-tolerance, though.
Please don't. It just adds unnecessary cost. Be realistic about what precision you actually need.
Surface finish, use standards like SPI or VDI. Differentiate cosmetic A sides from non-cosmetic B sides.
Yes. High polish means hardened steel, lots of hand labor expensive, textures add cost too, and usually need more draft. Specify how you'll inspect it.
Color seems simple, but needs specifics. PMS or REL codes.
Best practice. Maybe even a physical color chip for critical matches. And be aware some materials or fillers, like carbon fiber, might limit your color options. Often means black.
Okay, material selection. This feels huge.
It is. Can be 30–70% of the part cost. Need the exact resin type and grade. Thermoplastic or thermoset. What performance specs, strength, temperature resistance, UV stability, chemical resistance, any regulatory compliance like FDA or OHS.
And if you don't know the exact grade,
Give as much detail about the application and environment as possible. The molder can often help recommend something suitable. Also, mention flow characteristics, MFR or MFI. Affects how easily the plastic fills the mold, especially complex parts.
what about additives? Fillers like glass or carbon fiber?
Specify them exactly. Percentage of glass fiber, for instance. These affect strength, stiffness, but also mold where glass fiber is abrasive. Might need harder tool steel like H13 instead of P20.
And colorants, UV stabilizers, flame retardants.
All need to be specified up front. Adding something like a flame retardant later can cause processing issues or affect other properties. Early communication is vital.
And shrinkage. Plastics shrink when they cool, right?
They all do, but different amounts. Depends on the plastic type, additives, processing conditions. The molder needs to account for this in the tool design to ensure the final part dimensions are correct. Providing specific shrinkage data, if you have it, is really helpful.
All right, shifting gears to the mold itself. The tooling. Big investment.
Major investment. First question, new tool. Or are you transferring an existing one?
If it's a transfer.
You need to provide all the details.
Yeah.
Mold drawings, maintenance history, cycle count, material it last ran, sample parts. The molder needs to check its condition and if it fits their machines. It's not automatically cheaper. Modifications might be needed.
Mold material. Tool steel versus aluminum.
Depends on volume, plastic type, required lifespan. Aluminum is faster and cheaper to machine, good for prototypes or lower volumes, but wears faster. Steels like P20 are workhorses for medium volumes, H13 for high volumes or abrasive materials, stainless steel for corrosion resistance or high polish.
So you match the mold material and design to the expected number of cycles, like the SPI classifications.
Exactly. SPI Class 101 for millions of cycles down to 105 for prototypes. No point paying for a million-cycle tool if you only need 10,000 parts, and vice versa.
Number of cavities. Single, multi-cavity, family mold.
Trade-offs there. Multi-cavity costs more up front, but lowers the per-part price for high volumes. Family molds make related parts together, but need careful design for balanced filling. Your EAU, estimated annual usage, helps determine the sweet spot.
Okay, critical mold design features. Runners, hot versus cold.
Hot runners keep the plastic melted right up to the part cavity. Less waste, often faster cycles, good for high volume, but the mold costs more initially. Cold runners are simpler, cheaper mold, but you get that runner scrap, longer cycles. Good for lower volumes or frequent material changes. Specify if you have a preference.
Gate type and location, where the plastic enters.
Big impact on cosmetics and part strength. Edge gates, sub-gates, pin gates, lots of types. You might specify a location to keep it off a cosmetic surface, or let the molder recommend based on flow analysis.
Ejection system getting the part out, usual pins.
Most common. But pin marks might be unacceptable on your A side. Then you need alternatives, like stripper plates or sleeves, which adds complexity and cost. Communicate cosmetic needs early.
Cooling design seems critical for cycle time and quality.
Absolutely. Control shrinkage and warpage. Standard cooling lines are typical, but if you have thick sections or need fast cycles, you might discuss conformal cooling, which is more advanced and costly, but very effective.
Venting, letting air out.
Essential. Trapped air causes defects like burns or short shots.
Vent locations and depths are critical, especially at the end of flow paths.
And those complex actions for undercuts, sliders, lifters.
Yep, significantly increase mold cost and complexity. Make sure all undercuts are clearly identified. Sometimes a small design change suggested during DFM can eliminate the need for complex actions and save a lot of money.
Using standard components like DME or Hasco.
Good practice. Ensures quality and makes future repairs or replacements easier, especially if the tool might move between different molding facilities.
Okay, nearly there. Production volumes and scheduling.
Need your EAU, your initial order quantity, and how often you expect to place orders. Volume drives everything from cavitation to material pricing. Small, frequent runs mean more setup cost per part.
Project timeline, realistic dates for samples and production.
Please be realistic. Mold builds take time 4 to 12 weeks or more, depending on complexity and material. Rushed timelines just stress everyone out and might increase costs or lead to compromises.
Quality assurance. What certifications does the molder need? ISO 9000 Year 1, ISO 13485 for medical.
Specify any required certs. Also, define your general quality standards, cosmetic appearance, functional tests. Boundary samples for visual criteria are super helpful.
Inspection needs. FAI, PPA, CMM reports.
Define the level of documentation. First, article inspection. PPAP level if it's automotive. Do you need CMM data for critical dimensions? SPC during production. Certificates of conformance. Be clear up front. More QA means more cost, but ensures parts meet spec.
Right, avoids arguments later. Lastly, post-molding stuff.
Anything after the part comes out of the press. Assembly, painting, printing, installing inserts.
Each needs its own specs, right?
Yeah.
Assembly drawings, paint codes, artwork files, insert types.
Absolutely. If they're doing assembly, provide drawings, a bill of materials, maybe even standard operating procedures. For painting, specify the paint, color, thickness, masking needs. For printing, provide vector artwork, location, colors. For inserts, specify the type, size, location. All adds cost needs to be in the RFQ.
Wow, okay. That is a lot of detail, but it really paints a picture of why it's so important.
It really does.
So, wrapping this up, the big takeaway is clear. A detailed, comprehensive RFQ is your absolute best friend in injection molding. It saves time, saves money, avoids frustration, and helps guarantee part quality.
Couldn't agree more. That upfront investment in gathering and communicating information pays off massively down the road.
Think of this deep dive as getting you prepared for that critical first step. The better the information you provide, the smoother the whole process will be.
It really builds the foundation for a successful project and a strong relationship with your molder.
So reflecting on all these details we've covered, from CAD files to cooling channels, what specific area of this whole quoting process do you think warrants its own deep dive next time? What leaves you curious?